In this video, we're going to discuss the Chow test. Chow test is designed to be a test of structural change. Specifically, you use the Chow test if you want to determine whether the parameters of an equation are the same in two different subgroups of a population. For example, you might be testing to see whether an equation is the same for males and females, whether the behavior of individuals are the same during peace and wartime, or whether people behave in the same way before and after a policy change is implemented. So ultimately, what we're testing here is whether the equation is different in these two subsets of the population. The first method builds on the dummy variable techniques that we talked about in the last video. And what we noted there is that including a dummy variable allows you to test for a difference in the intercept of an equation, or can be used as an interaction term with a variable to see if the slope of an equation differs for some subgroup of the population. Essentially, the first method just builds on that by testing for differences in the intercept and the slopes simultaneously. So what you do first is you define a dummy variable that equals 1 in one subgroup and is 0 in the other. For example, a gender dummy variable, or a time dummy variable for the periods where some different condition applies. Then you estimate an unrestricted version of the model that allows all the parameters to be different between those two groups. And to do that, you have to include the dummy variable, and you have to create and include interaction terms between the dummy variables and all of the independent variables in the underlying equation. If the original equation had k-slope variables and one intercept term, the new equation will have those k plus 1 parameters plus a dummy variable and an additional k interaction terms for a total of 2 times the quantity k plus 1 as the number of parameters in this model. Essentially what you're doing is you're allowing the intercept and each slope to be different in each of the subsamples of the model. The restricted model in this case is one where you do not include the dummy variable or the interaction terms, so you're restricting the parameters to be the same. There will be k plus 1 parameters in this equation, the k-slope variables and the one intercept term. Then you simply perform a wall test to test for the joint significance of the coefficients on the dummy variable and all of the interaction terms. So in this case, there are k plus 1 parameters that you're testing, so the degrees of freedom for the numerator is k plus 1 in the wall test, because there'll be k plus 1 restrictions, all of the form that the coefficient on the dummy variable and each of those dummy variable interaction terms will all individually be 0. The degrees of freedom in the denominator of the walled statistic would be n minus the total number of parameters in the unrestricted model, which is n minus the quantity 2k plus 1. You'd reject the null hypothesis if the F statistic exceeds the critical value at the preselected significance level. So this is one way of doing it. Another method, which may seem a little bit easier but will be a little bit less informative, will also give you exactly the same walled test statistic. And that method involves sorting the sample into the two subgroups corresponding to the values of the dummy variable being 1 or 0, estimating the equation separately in each subsample, and saving the error sum of squares for each of those. You create a new unrestricted error sum of squares by simply adding the error sum of squares in these two equations. And essentially, this will be the same as the unrestricted error sum of squares in method 1, because you're allowing all the parameters to be different between the two subsamples, as in method 1, when you use the dummy variable and the interaction terms to allow for all those parameters to be different. And then you estimate the parameters in the restricted version of the model where the parameters are the same using the entire sample. And then again, you perform a wall test, and this gives you exactly the same value as in method 1. So this test is a little bit easier because you don't have to create all those interaction terms. However, it'll also give you a little bit less information, because if you can reject the null hypothesis that all the intercept and slope parameters are the same, you won't know whether it's just one parameter that's different or all of them. An advantage of the first approach is you can look at the t-statistics on the dummy variables and the interaction terms to determine whether all the parameters are different or whether it's only one or a small number of parameters that differ between the two subsamples. Once you've conducted this test, you then have to decide what to do with it. In general, if it appears that all the parameters are different, in method 1, you could tell that by looking at the t-statistics on the dummy variable and interaction terms. In method 2, you can't really determine quite as much with this except for looking at the parameters, but you won't be able to tell whether they're significantly different without doing some further analysis. But if you do find that many or all the parameters seem to be different, then you'd simply estimate the two equations separately in each subsample, and when you report regression results, you'd simply report the equations separately. So if you find, for example, that the male and female earnings equations are significantly different from each other, you should just report the two equations individually. There's no gain from estimating parameters jointly. On the other hand, if only the intercept or a few interaction terms are significantly different, then you'd be better off using the entire sample and just including the dummy variable and or any interaction terms that seem to be important, because in that case, you're using the full sample to estimate the parameters that seem to be the same between the two subsamples. And that gives you somewhat more efficiency in estimating those parameters. So you choose whichever approach is most appropriate based on how many of the parameters essentially seem to be significantly different from each other. So the Chow test is an important tool to have because it tells us whether it's appropriate to lump the entire sample together or whether there's two different equations appropriate for different subsets of the entire population.